night before those dumb icemen get here. Yesterday they put the ice in the radio.
What'd you roll over in your sleep for? Where's that other chucklehead?
Hey, fellas! Hey, fellas! I'm stuck! Defrost me!
Welcome to Did You Know? The ESCO HVAC Show. We will see you in about 45 seconds or so. Make sure that you are subscribing to our channels, our LinkedIn, YouTube, Facebook. Turn on notifications, and we are very excited to be here with you. It's almost time, about 30 more seconds. Make sure to grab your notebook and pen so you can jot down notes along the way, because at the end of the show, you could have an opportunity to ask our guests questions so we can dive a little deeper into these topics. And here we go. Welcome to Did You Know? The ESCO HVAC Show. Well, welcome everyone to Did You Know? The ESCO HVAC Show. So we're going to have a little change of pace for this show. So we're actually broadcasting live here at the Habegger Regional Technical Training Center, just out there, just inside Indianapolis, Indiana, just inside 465. And we're doing a live show, and we actually have a class with us today. Everybody say to the rest of the world. And as everyone's popping in, just let us know in the chat where you're joining in from. We'd love to know where you're at. Are you here in the U.S.? Are you abroad? And if you have any questions, let us know as well. So we're joining today with my good friend, Dirk Nauman, who is an educator of the industry and really has a passion for developing training and training modules, and he sees how our industry is progressing. And we're really bringing in a lot of new technologies for training, right? So we have been talking about changes in the industry as far as new equipment ratings and new refrigerants and trying to get learning modules. We've had the Department of Energy, really making a presence on helping education of the industry on where things are going. So here at ESCO, we always try to provide materials for our educational programs. And Dirk is a great partner of ours. HVAC Simulator is a partner of the ESCO Institute. And we have e-learning modules, we have the books, we have our handheld learning modules, which is what we're going to be talking about today, so that we have a variety of media for learning, because we've understood that not everyone learns the same. Where all of our educational programs were just based on hands-on learning experience, and a lot of times it was just learning in the field. So as technology has changed and the ability to create simulators has changed, we are now opening up opportunities to really look at training from a variety of aspects. So Dirk, really appreciate you joining us today. And yeah, this is going to be a fun show. It's a little bit different character than typical, but this will be a good opportunity to see some things hands-on and still go through our educational. So let's talk a little bit about what we're doing today, Dirk.
So part of the students have what's called the desktop simulator. It represents the Bryant Carrier brand furnace, and it has live voltages in it with 16 heating faults and 16 cooling faults. So there's a curriculum that goes with it, but also there's a digital format, which we'll see here in a while.
Sure.
But this is how I use to project to what the students are doing with the curriculum. The curriculum follows both of them, but not only is it to gain knowledge, but it's to help people technicians become more proficient with their tools.
Absolutely. All right, so we're going to be focusing on electrical sequence of operation. So yeah, let's take a look at what we got. We got a simulator we can take a look at to see what our students are actually working with today.
So this is the desktop simulator. very compact and very portable.
So full electrical function of a gas-fired furnace, but in a much smaller package. All right, let's take a look, see where we're at.
So electrical sequence of operation. If I can get all the students to focus on the screen, please. So electrical troubleshooting is much more than just with your meter. We need to know component functionality. We need to know the sequence of operation. And there's a component sequence of operation. We talked about that earlier. It's a call for heat. The inducer begins. Then the pressure switch closes. Then the igniter, gas valve, flame rectification, and the blower. Hopefully I got that right.
Sounds good.
But there's also a lot more going on before the call for heat, and this is the electrical sequence of operation. And there's a connection diagram and a schematic diagram. A connection diagram, another name for that is a pictorial diagram. A schematic diagram, another one is a wire diagram. Or it may be called a, what else? What's the other one here? I know there's two of them, sorry. But we can go through these, and what we're going to see here is the right-hand side populates itself as the left-hand side is automatic. So the schematic diagram, it flows through the door interlock switch. Then it flows through the IDR. What's IDR? We see this, but what is it actually?
Right. Anybody?
Anybody?
IDR, when you see it on the wiring diagram.
So this exercise is learning how to read schematics. We see all these symbols on there, but what is it?
What do they do?
Yeah, it's inducer relay. And there's a key, you can go look at it. So it's inducer relay. But then as the power flows down, it goes to BL1. We can see definitively that the power flows to the blower 100% of the time. There's not a relay there, so therefore we know what? It's a ECM motor. You know, that's one of the universal truths of a ECM motor. And then as we flow down, it goes to our EAC terminal relay. Then as it continues, it goes to the transformer. Transformer induces 24 volts. It consumes power, and therefore it must return back to its source. The blower motor module needs to return back to its source. And then we create 24 volts. It flows from the transformer to SEC1. It flows through the trace. Magenta is a trace on the board. And then it flows through the fuse, through PL16. It breaks off, goes to an input to the CPU. The CPU says, hey, I see this, therefore I can continue. It's just an input. Then as we flow up, we go to a blower relay. That's where the blower relay gets its voltage from, through the limit string. I'm going to go quick through here. I'm not going to explain every component in the limit string. Then we go to PL18. It's an input to the CPU.
Input to our processor.
And then it goes to our terminal. So if a limit string breaks, what happens? We lose power.
That's right.
So it does not mean it's not a bad thermostat, but then it flows up to the thermostat. Then we have a thermal switch, and then as it closes, it comes to W. That was the first sequence of operation. So I asked everybody, what was the first sequence of operation?
Sure.
And what was the response? Call for going on before.
A whole pre-sequence.
All right. And so this is what the whole sequence of operation is. And this video goes through, and then we get a call for heat, and goes to the CPU. The CPU makes a decision, right? It's an if-then statements. That's all a CPU is.
Sure.
If-then. And then goes to PL12. It branches off in parallel, the low pressure switch, high pressure switch. And then the next sequence after call for heat is inducer. That relay closes these inputs, therefore I can move forward. So therefore, the inducer kicks on, and then my pressure switch will close. Both of them closes. They go to PL13, PL14, and we go through the sequence, and the CPU gets the inputs. Looking at the limit string on the connection diagram, all we can see is PL16 to PL18, right? At least PL16, it goes through the string, comes back out. Looking at the connection diagram, we cannot tell where the power comes from. We cannot tell where the power goes. But when we look at the schematic diagram, we can tell exactly where the power goes. So we need just to take a look at the schematic diagram. That should be one of the first things that I preach to technicians. When you go to diagnose, to evaluate, find that schematic diagram first thing, and just get in the habit of looking at it. because there is not any difference between a residential furnace schematic or a rooftop schematic. It's just following the flow of electrons. And then this will self-populate, the gas valve will come on, and we'll go through this. And I always ask, which one's easier to read? Where do your eyes gravitate to?
I know, and so that's always the big question when we're trying to teach understanding wiring diagrams. Are you a ladder kind of a technician, or are you a line kind of technician? So that's a good one. Depends on which way you like to see it, right? So when I look at a diagram, I typically start with my control voltages of my transformer. So a lot of times I'm going to gravitate to the right so I can see where I'm at, but then seeing where they're connected, I'm going to need my left side as well. So it's understanding both of them, but I've met technicians that prefer starting with a line and technicians that prefer starting for a ladder. It's the importance of knowing that they both go hand in hand and that you're going to need both of them to be able to trace the entire circuit out.
You never have to chase a wire through the harness all the way to the back of the blower cavity.
You know, I don't know how many times as a young technician when I was working on a piece of equipment, I'd spend an hour chasing down a red wire, an orange wire, a green wire, going, okay, I know it's on this wire, right? I see some head shaking. Don't tell me you haven't done it. It just kind of comes with the territory. Well, when you stop and you look at it, if your eyes can be retrained to visualize it, that's where a trainer comes in handy like this, where you can actually put it all right in front of you in one location. And now you can get your meter. Because really what Dirk is helping you understand here is that your line diagram and your ladder diagram are going to go hand in hand. And you're going to be able to look at the entire sequence. You can follow a sequence of operation when you understand how the two of these go together. So now, instead of just taking a wiring diagram and studying it, we're basically taking the wiring diagram and adding all the functional components into one small place. So you have a functional furnace in front of you. You've just never looked at it on a single plane before. So I love the idea of putting that trainer right in front of us, Dirk.
So yes, in the curriculum, it follows the sequence of operation. It follows the curriculum as your ladder logic, your schematic diagram. It follows all the way through. So by the time you get done with this curriculum, you will know how to read a schematic diagram. We're going to actually be having them draw a schematic diagram of a 60% furnace. So this is going to be interesting.
Nice. I like it. So we're taking the whole component, our wiring diagram, all the colors of our wiring that is in, we're putting them into one small location so you can sit at your desk and actually work on it instead of being on an actual gas furnace. So let's think about it like when we're in trade school. How many times have you had the opportunity to work one-on-one with a piece of equipment in training? Some, right? A lot of times we're maybe in a small group huddled in front of a piece of equipment trying to really see it, right? So hopefully you're the person that's right in front and you get the first-hand perspective. A lot of times you're going to be on the sides. So we're given the opportunity to look at a piece of equipment directly in front of you so that you can keep your hands in one location with a meter and not be going all over the piece of equipment. It's a fantastic functional item. All right, so where we're going to start today?
So not only is it sequence of operation and schematic reading, there's one important component that we need to know in order to be a proficient technician. Does anybody know what that is? It's on the screen. What the heck is potential difference? All right, a lot of people get this. Is the switch open or is it closed?
Right.
I remember struggling with this.
Yep.
But you know, what's a volt? It's not power. We see it on our meter, and this is the point I want to make to everybody, to all technicians out there. We see this on our meter, but what does it mean? You know, don't just take it for granted what it is. Stop to think, what does it mean? What is the why behind the what? So, simply put, voltage is what? Pressure.
The old water analogy.
It is, and guess what? Were you looking at my PowerPoint slides?
No, where are we at here?
So.
Oh, all right, now we're getting somewhere. Now we're using my kind of analogies. I love to paint by crayon, so now we're getting there.
So when we talk about pressure, what do we normally think of? Tire pressure? Water pressure? You know, we think of PSI. A volt is just a term. That's all it is. So if we have P1 on the gauge equal 120 and P2 is 120, what's the differential pressure across the gauges? 0. 120 minus 120.
No difference.
Your meter is just subtracting. It's a calculator when it's on voltage. That's all it's doing. So if we were to break that pipe, what is my potential difference across that pipe now? From P1 to P2.
I have a big difference, don't I?
So please be following this in your curriculum. There's questions there. Just turn the pages, please, to a few pages ahead.
I'll upload some of these pages too into the after edit so we can actually see those pages. Look.
Okay.
A few of them, not all of them. Just go to buy the book.
So now we're going to move to a switch. Test point 1, test point 2. This is a thermal switch. So the potential difference across TP1, TP2 is 0. Why? Because the switch is closed. 120 minus 120. 120 volts minus 120 volts is 0. What would the potential difference be to earth ground from TP1?
There's a
120, because now earth ground is our ground reference point. Now, what if the switch is open? We go across the switch, TP1 to TP2. The switch is open. Right, because we're 0 on TP2. From TP1 to earth ground, what would the potential difference be?
120.
And TP2 to earth ground?
0.
Correct. Just because you have 0 volts does not mean you will not get bit. All right?
It's potential.
So, potential difference is a fundamental concept that must be understood to be proficient at diagnostics.
How many of you, when you first got into understanding electrical, were shown or taught voltage from ground to a hot point along the way, and just shown to follow the lines just as a ground source? Unfortunately, it's common in our industry to be taught the only use of just going to a ground and not learning what that potential voltage difference is across switches and across loads. So it's very important to understand what that potential actually looks like. Yeah, good stuff.
So continue on with potential difference. There's a lot of exercises with the simulator. This was demonstration there. We're not going to go through these, but please, when you get this on your own time, go through these. There's some trick questions in there, but I don't have them on the PowerPoint. But the answers are always given to you. But again, let's struggle through before you turn the pages. So, but I do want to ask this question here: is there any situation where an open switch would have a potential difference of 0?
Yes.
When?
Power's not on.
Very good. Excellent. So we always think open and closed switches, open switch, always going to get a potential difference across it. But if you don't have power to it, you go both sides, all three of them are going to read 0 from each side to ground and across it. So, okay. What do you think?
Yeah, doing good. So tell us a little bit more about these practices with our simulator. So how many practices have we got on the gas furnace? What all can we do with the simulator in comparison to standing in front of the actual gas furnace?
So there's 16 faults in the simulator.
Okay.
They range from whether it's the open winding on the blower motor, open pressure switches. The first 4 are just static.
Sure.
They're really easy just to get familiar with it, you know. So if everybody would turn their dials to 1-1. And now I want to explain this push button.
Sure.
So if you look, and on the digital in the back, there's a digital simulator. Actually, I can just go to that right now.
Sure, yeah, let's take a look, see what we're looking at here.
Excuse me. So we have a digital. We're going to be on 1-1. So on the digital, there's a push button also. So the push button acts as a service switch on the side of it. It also starts the fault sequence. So if we hit the push button, everyone should be on 1-1, give it a call for heat, and hit the push button. The inducer motor should come on. Is that correct?
Yeah.
All right. And then something's going to happen. I probably should have given a clue here. Mm-hmm. Everyone in the back, please do this. there's yellow markings on the side and the top.
Indicator
Pull
light.
that out. So as I preach, we need to have schematic diagrams. This will be your schematic diagram with all of the fault codes. So by now, I would think your simulator is flashing a light, correct? This fault code is to the manufacturer fault code. So there's a process. Everything has a process to it when you're diagnosing. There's actually a process. All technicians should have a process before they even get to the door. There's a process when you knock on the door. There's a process when you talk to the homeowner. There's a process when you start to diagnose. So Gary Lloyd wrote a wonderful book back in the day. He was a RSES member, and Gary wrote Tech Method. Have you ever heard this book? I have. So ECH, thermostat, evaporator, condenser, and H is enthalpy, which is your heat. Always go to the Clifton. How many times did you go straight down the furnace and you diagnose it bad batteries on the thermostat? You ever done that?
Might have been a few times out there. Might have been quite a few times out there.
So follow the process.
That's right.
Always go to the thermostat first and then go to the furnace. So we're at the furnace. What did not happen in the sequence of operation? We have a call for heat. The inducer came on, but what did not happen?
Gas valve not open. Oh. Says
So mine timed out, and everyone hit that push button again. Everyone hit the push button. It starts the sequence over, and we can do this on the digital. So we can see the red light, the indicator lights. The indicator lights represent what you can see and or hear in the field. Inducer, we can hear it. The igniter, we can see it. But the igniter is not turning on, right? It's not energizing. You on 1-1? Okay, just jump over if you would, please. You got a call for heat? Turn your red dip switch on. Is that on? Okay, we'll take a look at it later. So what did not happen in the sequence of operation? Anybody? Pressure switch. The inducer came on. Hit the push button again. If the inducer is on, the pressure switches should be closed.
yes. I'm thinking the gas valve's not coming on. I wasn't reading.
All right, let's go through this process. So I'm hearing multiple possibilities here. Let's go through the process. We have a call for heat. Let's check W to C. We have 24 volts potential difference across, therefore we know we have a call for heat, right?
Correct.
Let's check the inducer. That's the next sequence of operation, the next component. So it's going to be PL2. So the inducer, that's PL3, excuse me, PL3. So we have power of the inducer, correct? The light's on so we know it's running. And then the pressure switches. Here is a key component that I always teach people. So now I have potential difference because my inducer is off. But I'm going to hit the push button. So the pressure switch closes. Inducer's running, closes. After that, what's the next sequence of operation? My igniter does not turn on. So let's reference the schematic diagram. I have the schematic diagram built into the digital. And I always teach technicians to start at the component and work backwards. So we look at the igniter and we work backwards. We have a hot surface igniter relay. And then as we work backwards, we have inducer relay. If the inducer is running, then we have power sitting at the hot surface igniter relay. There's only two possibilities. Two. It's either a bad board because of relay in the board or a bad hot surface igniter. So let's take a look at it. So the process is to follow the sequence of operation, call for heat, check the inducer, check pressure switches, and then the igniter. So we have, I'm just going to jump forward. So we have 120 volts going to the igniter. Correct? The igniter is not glowing. Therefore, we check the component. How do we check hot surface igniter? Resistance. You should have OL on your igniter. Is that correct? So for proficiency reasons, if we follow the process, we will be dead on the diagnostic every time. Now, the root cause is a different question.
Sure.
Because pressure switches can be a little tricky. That's why when I tell everybody, when you're checking pressure switches, the most important tool to have, to me, is needle point meter leads. Because now you cannot get into these Molex plugs.
Sure.
Pressure switches are so sensitive. If you pull the tubing off of it or you pull the wire off, you have a high probability of a callback. Why? Because you changed the state of it, you put everything back together, and guess what happens? It works.
I'll be darned. Had a couple of those. Have one?
So, follow the process. Make sense? What do you think?
Hey, I'm liking it. Pretty good stuff. Anybody got any questions right here? So are you seeing that we're just taking the entire layout of a furnace? We're grabbing all of the functionality of the components. We're grabbing our line diagram, we're grabbing our ladder diagram, putting them next to each other, which a lot of times, depending on the manufacturer, they're going to be in that representation. So what you're seeing in front of you is a blown up wiring diagram, but now we've added all of the components, the mechanical components, to the electrical schematic so that you can see through the entire electrical troubleshooting. So yeah, a lot of really good stuff there. Dirk, where can we find more information about the HVAC simulators and the things that you're doing in electrical simulation and mechanical simulations?
So HVACsimulator.com is our webpage, and we have a few products coming out. We're going to have a product where you can put any single stage manufactured board on there, and all the components are out there, so it doesn't matter the board. We have near field communication coming out, on the Carrier Bryant line.
Sure.
I know it's out there in other manufacturers already, so, but it's something that you can take home, you can learn on your own. So I call it the after-hour sacrifice.
Sure.
If you want to advance in this field, then it requires to learn it, to practice it, and it's not at the customer expense. I want to stress that we were talking about this a little earlier, that of all the trades out there, which one's advancing more quickly than any other trade? I think it's HVAC. There may be other ones out there.
Sure, it's pretty significant though, what we've seen just in the last few years.
It's insane what we're seeing.
Yeah.
So.
Do we want to go through any other practices while we're here, since we've got everything up and live and running?
Yeah, actually, let me kind of show another product.
Yeah, absolutely. Let's see what we got.
So we're coming out. You ever heard of the HVAC Excellence?
Oh, I might have known a little bit about that.
Okay,
just a little bit.
Okay.
They happen to have a conference in March 20th through 22nd in Las Vegas. And might be able to find more at escogroup.org.
So let's put a plug in for this. Let's put a plug in. For all
conference.
Instructors watching, please go to this. This is awesome. But anyway.
Yeah, Dirk's going to be at the HVAC Excellence National Education Conference, HVACR National Education Conference, and we look forward to seeing you there. If you want to see some more live demos of the simulators, make sure to hang out with us and get a chance to hang out with Dirk and see his products and learn a little bit more about what's going on in the world of simulators.
So,
yes,
this is what I showed you earlier. This is the refrigeration simulator.
Oh, okay.
This thing's pretty cool. Pretty cool. So what is refrigeration diagnostics? What's the hands-on part of it?
Don't get burnt.
Don't get burnt. That's what someone else said.
Frostburn, but-
So, is it frozen?
Pretty much.
Okay. So,
We're melting or we're burning.
there. Yeah, either one. Yes.
So,
But we put the gauges on.
yep.
We put instruments on. What are we left with?
Numbers.
Numbers.
Okay. Yeah. absolutely.
Can you learn diagnostics, refrigeration diagnostics on the job? The answer is yes.
I hope so.
But it's going to take a lot of time. It's going to take a lot of time. You can't, it's data. How to interpret the data. So what we did with this, and I learned this from another trainer, the ABCs of comfort cooling, airflow before charge.
Yep.
Before you evaluate, before you diagnose, definitely before you charge a system, please check what?
Airflow.
Everyone out there in cyberspace, everyone get that? Check airflow, please. Airflow before charge. So what I did is I took live data. I created a data logger. I put all the data into a spreadsheet. I wrote macros, and then I imported it into this trainer here.
Okay, so we can evaluate numbers live.
Correct.
Yeah, okay.
This is live data here. Even though we're not on the job site,
Right.
we can make diagnostics from this. We can pause it, the data. We can look at graphs. But then we can change the blower speed.
Okay, so we'll be able to adapt the scenario in live. So we're not having a complete functional system that we're making changes to. We can make mechanical simulated changes.
Correct.
In a working module. Okay.
Yes, so we look at airflow. With excessive airflow, does it create more BTUs or less BTUs? What do you think? More.
Oh, we're talking about heating.
No, we're talking about air conditioning.
Air conditioning, no.
Yes. Higher airflow produces more BTUs. And we can see this as we go down the speeds, and we can see what the pressures do as we go down. We can see as we drop the blower speed, we can see the pressures come down. But to learn refrigeration diagnostics, it's a study of the refrigerant.
Sure.
That's exactly what it is. So in the curriculum, what we're going to do, you're going to have 5 blower speeds here, and you're going to fill out a diagnostic chart that has the refrigeration circuit on there, same thing up there.
Yep.
And you're going to and you flip the pages. And there's these, you ever seen the chart out there for up arrow, down arrow,
Oh, yeah,
subcooling?
absolutely.
I reference it all the time.
Yeah.
But here's the twist with this one. You have to fill it out. So you have to
So
go
you actually have to
reference-
put the data in.
Yeah, you got to put the arrows in.
Okay, now we're getting.
But yeah, but you have to compare the high airflow, and you go
Yeah.
through the 5, and you can actually see it go down. You can see what the suction pressure does. You can see what the superheat does.
Sure.
So, but yes, and as we go through with the low blower speed, you can see that the total capacity down at the bottom is lower.
Okay, so online module then?
Yes. Yep. Yes, this will be on the ESCO.
Okay,
So we're going to be releasing this at the HVAC Excellence.
excellent.
So, and the reason that is because now I have 3 months to get it done.
Yeah. All right, so we have a variety of options. So we've got online education. So we have the opportunity to do functional modules and e-learning capacities. How many like doing e-learning modules? Is it something you're starting to become more aware of and more used to? Because there was a time not very long ago where books and hands-on in front of pieces of equipment was really the only option that we had. And then we all seen some changes a couple years ago around March of 2020 where that completely went to the wayside, right? And we had no hands-on education, or we had very limited. So it started the development of things like our HVAC simulator, handheld electrical simulators, and now online learning modules. So we're going to see a lot more of this going forward. And Dirk, I really thank you for joining us today, diving into the product, showing a little simulation of what it's going to look like. And anyone in the audience have any questions for us today before we hop out of here? Variety of people joining us. Nigeria.
Nice.
Yeah. Cleveland, Ohio. Thanks for joining, Kathleen. All right, well, I think we'll wrap it up today. So a little bit different show than we're used to, but we wanted to give you a live perspective of what these simulators look like, be able to see what training is progressing into. So we have other avenues of training besides just manuals and just e-learning modules. Now we have hands-on physical representations of what equipment actually looks like while it's functioning electrically. So we're going to hop out of here, and we thank you all for joining Did You Know, the ESCO HVAC show, and we shall see you next week.
Thank you.
Thank you for joining Did You Know? The ESCO HVAC Show. You want to see some of these great presenters in person? Well, then we'll see you at the National HVACR Educators Conference, where many of these guests will be presenting live classrooms, and you'll have a chance to interact with them. Would you like to watch this show again? Hey, no problem. Just head on over to YouTube to ESCO Institute. Do you have a topic that needs clarified about some kind of a change in the industry? Well, then let me know. See Beck at escogroup.org and we'll see what we can come up with.